air conditioners, and heat pumps are all essentially the same process. And they are also essentially heat engines running in reverse. So remember, with the heat engine, we had our hot reservoir, we had our cold reservoir, and then there is, work being done, mechanical work being done. Well, refrigerators, heat pumps, and air conditioners, we put work in order to move energy from the cold reservoir to the hot reservoir. So the same relationship exists, that Q hot is still equal to work plus Q cold. In the case of a refrigerator or an air conditioner, your goal is to make the cold reservoir colder. In the fridge, you want to keep what's inside the fridge warmer, and with an air conditioner, you want to keep the inside of the room colder. And so you're pumping heat out of the cold reservoir to make it colder. With a heat pump, that's like the heating systems in school or in your house or whatever. Well, actually, in your house, you probably have the floor heating, which is hot water, so that's actually a little bit different. But with the heating system in the school, and in most places in the States anyway, they operate their heat pumps. And that's the same process as this, except the goal is to make the hot reservoir hotter. In the case of air conditioning in the summer, the hot reservoir is just outside. The cold reservoir is the room, and you're making it colder, putting in work to yank energy out of the cold reservoir to make it colder. For a heat pump, the hot reservoir is inside and the cold reservoir is outside, and you're trying to make the hot reservoir hotter. And a refrigerator is exactly the same as air conditioner. So anyway, all three of these operate the same. The only difference is that a heat pump, you care about the hot reservoir getting hotter, whereas with a refrigerator or AC, you care about the cold reservoir getting colder. Yeah. If you, an interesting facet of this is that, for example, when you, if you take like a window unit, a window air conditioner unit, and you don't put it in the window, you just kind of put it in the room and run it, the temperature in the room is actually going to increase, because there are parts inside, there's parts inside the air conditioner that generate friction, so it actually gets hot inside there, and you're turning work into heat. And so actually you wind up raising the temperature of the room if the thing is fully enclosed in the room. Those standing units have some kind of hoses connected so that they are connected to the outside, and so they are able to yank heat out of the room. Now that might be confusing because a lot of times air conditioners will also have a fan in them, so it seems like cold air is coming out. But what's really happening is that air is being taken into them, and then the heat is being pulled out of the air, essentially, and pushed outside, and then a fan just blows that cooler air back into the room. So it's not producing cold air exactly. It's pulling in hotter air and making it colder and then blowing it back out. Yeah. So typically for refrigerators, air conditioners, and heat pumps, unlike a heat engine has its efficiency, the rest of them, for these three, they have what's called a coefficient of performance, which is often abbreviated COP. That's not a policeman. Yeah, it's the coefficient of performance. For a fridge, or the AC, the coefficient of performance is equal to Q cold over work. It's how much heat you're taking out of the cold reservoir, because this is what's important, is how much heat you're taking out of the cold reservoir. For a heat pump, the coefficient of performance is Q hot over work, because what you care about is how much heat you're putting into the hot reservoir. Just for a fridge, the coefficient of performance is typically between 2 and 6, apparently. Yeah, I just looked that up, and that's what the internet told me. An ideal reversible heat pump, fridge, any of these, remember they're all the same thing, has the Carnot relationship that we discussed last time, where the work is equal to Q hot times 1 minus T cold over T hot, and that's because Q cold over Q hot is equal to T cold over T hot. Okay. So that Carnot relationship exists for a reversible fridge, air conditioner, or heat pump. Problems you do with these are exactly like they are for heat engines, so I'm not going to work through an example here.